So what we've done is we're going to add a capacitor. We're going to use a capacitor filter. And this is not in the textbook, but what's going to happen is that, let's see if they show a better picture of this. Huh? Oh no, I keep sorry guys, thank you. So what happens is we went from this for a halfway rectifier. We call this pulsating DC. And the pulsating DC is at the same frequency as input AC, right, for a halfway. So if we had 60 cycles coming into a halfway, then the output would still be 60 cycles, right? What we did though is so the power supply, we're going to have AC coming in. We're just going to draw the symbol. Of course, we know we probably got a transformer. And then this would be a positive supply, so that means the anode is going to point toward the source. And then what we're going to do is this is the circuit that we've been looking at for quite a while. And the worksheet was on this. And the test is on this. Well, what we're going to do now is we're going to come up here and we're going to add a capacitor. And we're going to use what they call electrolytic capacitor, which is a polarized capacitor. I take it like this, I think. It might be an E right there. Let's look it up. And normally electrolytic capacitor, we draw the positive plate with a straight line, and then we draw the negative plate with a curved line. And then no matter how it's marked on the capacitor, we usually mark the positive side. And we looked at a video last time, and if you put the thing in backwards, what's probably going to happen? Yeah, very interesting. So these guys are designed to reduce the size of the plates by polarizing the plates on them. So what happens now is that, of course, we know the transformer has an R component, and the diode has an R component. These are very, very small. So what happens is we know this thing charges time is equal to, what's the formula? RC time constant. And we know to fully charge it, it takes at least 5 time constants, but we're never going to do this. We're not even going to get close to that because as soon as it starts discharging, well, I'm sorry, the time it takes to fully charge it, or the time it takes to fully discharge it is 5 time constants. So it don't make any difference where you go. But what we're doing is we're not even letting this thing get close to 1 time constant. 1 time constant is 63%. But then the next time constant would be 63% of what's left, right? You understand? And the next time constant would be 63% of what's left. So what happens, the capacitor would charge in what we call an exponential curve. Right? Up in here, this would be 63%. Yeah, probably close to it, or right around here. So what we're going to use is on the capacitor discharging or filtering a power supply, we're not even going to use the 5 time constants because we're not going to ever let it go 5 time constants, right? In fact, we're not even letting it go 63, but it's close enough to figure out what the actual thing's going to be. So that means if we're going to calculate this, then I can come over here and I can say my time is equal to R times C instead of R times C times 5. Okay. But what we want to do is we want to calculate, so what's going to happen, of course, is it's going to charge up, the diode turns on, it's going to charge up, right? And then as soon as it drops down, the diode is going to turn back off. So the diode is only on for a very short period of time. Just long enough to do what? Charge it. But it's going to be charging through almost all very, very low resistance. So if we look at the rating on the 1N4000 series, we found out that this guy right here can handle 30 amps for one cycle. So it has no problem, even though it's rated at 1 amp, it can handle 30 amps for one cycle. And that's what we got here, right? You understand that? Or probably even a lot less than that. So we charge it up and it discharges. Well, when it starts discharging, this guy right here turns off. And then now what happens, I have a positive here, I have a common there. So now the capacitor is allowed to discharge through the load. But as soon as it starts discharging, then we have this guy over here, right? Understand? Does that make sense? The resistor in ohms. And the size of the capacitor in farads. So farads are rated is the size we rate capacitors. Now, why don't we rate capacitors in ohms, even though they have an opposition? That's a good test question. Well, that's not why we don't rate it in ohms, but that's why I don't do any power. So that's why I don't dissipate any power. So why don't we rate it? Because the ohms varies with frequency. Well, that's a great question. So you can't say it's 200 ohms because it might have 200 ohms at 500 hertz, but as hertz goes up, frequency goes down. So this is why it's rated in a unit called farads, and that's its ability to store a charge. Farad, it's capacitance, but the capacitance is in farads. So the opposition, we call it reactance because it changes resistance. And this is the formula, and this is something that we're not going to use in this class. It's 1 over 2 pi, which we use 6.28, times the frequency times C. So right off the bat, for a certain size C, as frequency goes up, the opposition goes down. And as frequency goes down, the opposition goes up. So if you got a frequency of 0, what would be the opposition of a capacitor? Huh? Well, technically it would be infinity, but it never is because there's a dielectric in there. Yeah. So anytime you divide a number by 0, y'all know what division is? No, division is subtraction. So what we do is we come out with a number, and then we subtract. We see how many times I can subtract 5. And so I would come up with 20, and that's what it is. And then I subtract 5 again, and then I would come up with 15, then I subtract 5 again, and then I would come up with 10, then I subtract 5 again, and then I'd come up with 5. Then I subtract 5 again, and I'd come up with 0, and then I subtract 5 again, and we can't subtract 5, so we count the number of times we can subtract. And that's what division is. And what is multiplication? Is repetitive addition, right? You understand? But instead of doing this, what we do is we learn multiplication tables so we don't have to do the subtraction. So we don't have to subtract the numbers and count how many times you can subtract before you can't subtract anymore. So that's what it is. So how many times can I subtract 0 from 5? Infinity. So any number divided by 0 is infinity. So if you do it on your calculator, it's going to pop up an error. Why? Because your calculator can't calculate infinity. So that's why. But most people, when you divide by 0, most people say it's 0, but it's not. It's infinity because that's how many times you can subtract, right? You understand? Until you can't subtract. And I can't subtract 5 again. So that means if L is 0, so technically a capacitor looks like infinity when it's in DC. Once it's charged. So that's why when it's charged, there's no more current through the resistor, through the capacitor, right? Does that make sense? It's pretty. But you'd be surprised, you could put that on a test. What's any number divided by 0, and more than half the class would say 0. Even though they got their calculator in front of them. Huh? In an open air DC circuit. So a capacitor will not pass DC once it's charged. So technically that's what we say. We say a capacitor blocks DC and passes AC, which is pretty neat. And we'll find out a big use for that in transistor circuit. So what we end up with is here the diode is on, right? You understand? Here it turns what? Off. Here it turns on. So here it's only on for that amount of time. And of course, as soon as it drops down, the diode turns back off. And so what's actually running the load during this amount of time right here is the capacitor. So the capacitor is literally running the load. So the more current that's required, the bigger your capacitor's got to be, right? You understand? So the load would determine what size capacitor. Everybody okay? So what we did was try to calculate this ripple voltage. So I start off with T is equal to R times C, and I need to get V in the formula. How can I get V in this formula? Well, and so what we can do is we can use what Ohm's law says R is equal to, right? You understand? So I could say T is equal to what? V over I. Huh? I'm listening. You don't see what I'm writing? Oh my God. I'm right here in green. Let me change color. What's that? I'm sorry, yeah. And then we would say times C. And then what are we trying to do is we're trying to solve for this voltage right here. So I need to rearrange this formula and solve for V. So how would I do that? Yeah. Because that's what we're trying to do. We're trying to solve for the voltage. And this is the actual ripple voltage. Well, we got rid of T. Okay. So no. So what we're going to do is we would have to divide both sides by V and divide both sides by T, right? So what we'd end up with is C would still be on the top, and then we would have T times I. I mean, that's the formula. If you actually look at it, it's on the formula sheet. But instead of using, no, I'm sorry. So I would still be on the bottom. Over here. That's not the formula here, is it right? Yeah, this is it. I just got to figure out what I'm doing. So C is still on the top, right? C is on the bottom. That's the right formula. Let's come out and figure it out in a minute. So we come out with what? What's the formula? We got two. We got what? And then, of course, we know that time and frequency is the reciprocal of each other. So this is probably the easiest one to use. It's I over C times F, right? So for halfway, we would use the input frequency. So down here we'd use 60. So let's come up with some numbers. Let's say my load current, this is the load current, by the way. So let's say the load current is equal to 200 milliamps. And then I'm using a C of 100 microfarads. So what would be my ripple voltage? We need for Alabama Power. Right now, yeah, 60. Yeah, that's a good point. Huh? So we'd say what? We'd say 200 milli, right, divided by 100 micro times 60. This should give us our ripple voltage. So you guys, you need to probably use parentheses, right? So how would we enter that in our calculator? Let me find my calculator. So I'd start off with what? 200 milli, right? Divided by, then I would do what? Open up parentheses on your calculator, right? Everybody okay? And I'd say 200, and then I'm finding my times 10 key. On this calculator, it's EXE times 10 to the minus. Don't use this right here. Somewhere on your calculator, you got a change sign key. So you hit the change sign key, and this would be a what? Oh, wrong. At the top. So I did it wrong. Yeah, I got it wrong. Sorry. I was reading the wrong numbers. So let me start over. 200 milli, right? 200 times 10 to the minus third, right? Then we'd say what? Divided by. Then I'd open parentheses, and I'd say 100, and I'd say 10 to the minus 6 times 60. Now I come up and close my parentheses, and then I say equal. Something's wrong. Ain't no way in the world that's going to be 33 volts. What did I do wrong? Huh? 60. You probably need to use a bigger capacitor. No, it's 33.3. You left off with 0. And that would be, huh? So we need a lot bigger capacitor is what it is, for 200 milliamps. That's what you do. That's what you get when you pull things off the top of your head. So let's change our capacitor to 1,000 microfarads. We should move it over 1 decimal point, right? Dang it. So this will be 200 milli, right? Divided by 1,000 micro, which I'm going to change this down here. And times screwed up. So 3.33 volts. Are we okay? So what that means is, I'm listening. I'm listening. Okay. So that means this peak-to-peak voltage would equal to approximately 3.3 volts. So if this peak value was 16 volts, what would my voltmeter be? What's that? So we got 11.3. Bernard says 11.3. Your guess is 11.3. Oh, really? Okay. So we came up with VR, what we call peak to peak, would equal to 200 milli, 1,000 micro, times 60, right? And when we ran through this, we came up and got 3.3 volts, peak to peak. Oops. No, it's I. Yeah, so the formula is V ripple P. What number is this on your form on your sheet? Okay, 17. It's equal to I the load over the size of the capacitor in farads the frequency in hertz. So if an R say 11.3 volts, my volts DC 11.3 volts. Yeah, I gave you that. Peak is not RMS. Yeah, and what has happened, guys, those values, basically, the formulas that we use for unfiltered are out the window. We're not using those anymore because these guys never go to zero. Never ever go to zero. So now we've got DC. This is DC. This is not pulsating DC. This is unregulated DC. And what do we mean by unregulated? So regulated means it's constant, right? Unregulated means it's going to vary with load. Because look at the formula right here. This sucker right here's got the current of the load right there. So what that means, and it's on top. So if the current of the load goes up, then my ripple voltage goes up, and if the current of the load goes down, my ripple voltage goes down. So that means, and this is going to set the average. This is going to set the voltage. So this is unregulated. This sucker varies with load. Varies with load, and we'll try to show y'all that when we hook up the circuits here. And this is the problem we have, but if I can come up here and set up a regulator that regulates down here, then I can get really nice DC, right? You understand? Because it'll cut off the top, and that's basically what a regulator did. So what your regulator is going to regulate at a voltage that's lower than what we're going to this value right here, this valley right here. So what's going to happen, guys, this right here is seen as we call it a ripple voltage. So what we did is we just calculated ripple voltage. This guy, your DC, is going to be average right down the center of this right here. Just like in AC. So the DC average of a sine wave is down the center, right? And we say it's 0 volts, so it's going to be down the center. So if we look at the voltage, the formula, what formula is this? Voltage DC, full wave unfiltered, half wave unfiltered. Well, the formula is the same. It's going to be what? Now, V peak out. V ripple peak to peak, which we just calculated, divided by 2. So what we would say, okay, my voltage DC would be equal to 16, which is what I gave y'all, minus 3.3 divided by 2.
Now, you said that E.
Yeah.
So that means if you multiply that by 2, you get E.
Only if I was dealing with, but we're not calculating the peak to peak voltage of the DC. We calculated the peak to peak voltage of the ripple voltage. So this is peak to peak. These formulas right here is peak to peak. So that's what we calculated, because we calculated from peak how long it took to discharge. Well, how long it took to discharge would be the peak to peak voltage. Yeah. So that's a really good question. So no. So here we don't even use peak to peak over here because we're already in DC, right? It's just that what we're doing is we're taking pulsating DC and converting it over to unregulated DC. And hopefully you understand on the division formula, if it's on the top, then the variation is directly proportional. So that means if you double your load current, right, you understand what's going to happen to your ripple voltage. It's going to go down 1/2. I should say the inversely proportional because it's on top, right? Okay. So anything on top on the right-hand side, if it goes up, your answer is going to go up. And if it goes down, your answer is going to go down. So if I increase the size of my capacitor, and we saw a perfect example of that, if I increase the size of my capacitor, my ripple voltage goes down because it's on the bottom, right? Does that make sense? So I can either increase my frequency. So this is why higher frequency has an advantage. So if I increase my frequency, then my ripple voltage goes down. If I decrease my frequency, my ripple voltage goes up. So this is why a lot of your switchboard power supplies are operating like 50 kilohertz. Because the capacitors don't have to run the load hardly any time at all, right? So it varies with what, and this is another advantage of a full wave in that for the same size capacitor, the ripple voltage is going to be less, right? I lost my, it looks like I lost my pen. what we're doing is we're doing this class, we're gonna do this lab in class. And so here's my half wave rectifier right here. Okay, here's our 12.6 volt center tap transformer, right? Y'all understand that? Well, here's a 2.2K. Here's the diode. You can actually see the cathode here, so the anode is pointing toward the source. And this is the circuit. And then of course what we're doing over here in the chart is, what did we do? We marked out, oops, wrong letters. We marked out where the author here said V load peak. We just marked that out and said V load. But these are computed. And then what are we going to do? We're going to fire it up and measure it, right? But you need the V secondary. They want you to do V secondary RMS. Of course, we need V peak to calculate it, right? So you okay? Everybody okay? So what we got for what do we have computed across the load? Anybody got it yet? It can't be, it's got to be less than, we got to be less. This is the V. This is DC. This is across the load. V across the load, this is DC.
Only across the load.
Across the load, that's what V is.
Also, that's VDC.
Huh? Yeah, this is both DC. Right. So we're, see right here it says what? V across the load, and what's across the load? DC. This says V across the load, so this is DC. So what we're trying to do is we're trying to compute the actual voltage we're going to get across the load. And I don't know why they're asking for V RMS across the secondary. We're going to use the measured value. So let's change this to V peak out, guys. Let me go ahead and do that. Because there's no reason to calculate it because it's given to us. So we're going to make this what? V peak. Yeah, because they don't make any sense, because they give us, and what I'm trying to teach you is that we're going to use whatever the transformer is rated at, and we know that our answers are not going to be perfect, right? Because the 12.6 volts is. So here they give us the rated transformer value right here, so it's no use for us to measure it, right? Does that make sense? And I can't write this down, guys. So what do y'all have for V peak out? So V peak out will equal to what? V peak minus 7. So we need V, before we get V peak out, we got to do V peak secondary, right? Should be equal to 12.6 divided by 7.7. V peak secondary right here. And then my voltage DC across the load would be equal to DC is equal to VP out, right? divided by 3.14. I think it's around, what, 5 votes, something like that. I did all that math in my head. No, I didn't. Yeah, so that's what I actually make this. This right here should actually be VP out. Yeah. And that way we can. Yeah. So what we're going to do is we're going to make this calculation right here VP out. And then we can go directly to the load, right? Compute it. And then I'm going to turn it on and put my meter across this and measure it. Calculations, what you got for what you got for across the load? Right here, this is across the load. What's that? Well, no, you're going to do this first, then you're going to do this second, and then once you get this, we're going to make the measurement. Right? That makes sense. So, okay, so we pick out would be what? 17.1? That's what you gave me a while ago, Brian.
Yeah.
And then the other low would be, what's that? No, the V peak out is it's after you subtract the 0.7. It's not going to be V peak out minus 7/10 of a vote. It's going to be V peak secondary minus 7/10. I'll look. So here's my calculator. So I've got 12.6, and I'm going to divide that by 0.707. That's equal. Didn't come out right. 12.6 divided by 0.707 equals that, minus 0.7 is equal to that. Yeah, so what you did is you subtract 7/10 from V peak out. So it sounds like you might have subtracted 1.4. Then I'm going to come up here and I divide this by pi, which means we're going to expect about 5.5 votes out. I can't do much about the glow, guys. I guess I could set it up here. So here we go, this is our measured value. Not too bad, right?
Right. Yeah.
I like that. So this is measured, we calculated 5.5 and we measured 5.1. That's only 400 millivolts, huh?
Yeah.
This is a halfway. Yeah, it's halfway, but only one diode. Anytime you see one diode, it's halfway, right? We're doing the first circuit, right? Y'all see the first circuit on the 32-2? That's the circuit we got hooked up. Of course, I've got all of them hooked up here. All I gotta do is just move my AC. Yeah, 5.1. Yeah, 5.13. I'm listening.
Wow, DC secondary. You just 12 months divided by.
Right. Which KV is 17.1 or something. 0.7.
What I want to ask you, secondary is about just like last, each number is right spot. What I usually secondary is 17.8 or what you said.
The VP secondary would be the 17.8. The V peak out would be the 17.1. So that's out of the diode, right? And we can literally see the little difference when we pop it up on a oscilloscope. We can literally see the small difference between. Yeah. So guys, here's the input. So on your drawing here, I think it's and what you're supposed to do, guys, is that when you make measurements for your oscilloscope, you're trying to make them as big as you possibly can do them and keep them on the screen. That's when your scope is most accurate. So here's the AC in. And we'll cross it right from the center where that's at. First of all, let's look at the time. So this guy would be 1, 2, 3, 4, 5, 6.248. 6.8 divisions. So 6.8 divisions, right? Then I multiply it by my time, 2.5 milliseconds. So what does that give you for the time for Everybody understand what we just did, yes, ma'am? What we're doing is we're measuring on the scope. This guy down here made. If I'm counting ones, there's 5 minor divisions between each one, so that means each minor division would be worth 0.1. I mean, I'm sorry, 0.2, right? You understand? So I come up here, I go 1, 2, 3, 4, 5, 6, right? I'm starting by negative to negative. How many divisions did I say? I think I was wrong. 1, 2, 3, 4, 5, 6. This would be 0.2, 0.4, 0.6. I'm sorry, 2, 4, 6. So I got that wrong. Then what we do is we multiply it by the time per division. And then when we multiply it, that gives us the total time, right? You understand? So what does this come up and give us? Huh? No, to measure a cycle, you measure from the same point to the same point. You can measure it at peak, but peak's real hard. So normally what I do when I'm measuring time, I use my horizontal position, which is this control right here, called horizontal position. And then I turn it from my left-hand side onto a vertical line. See what I've done? And then that gives you a point to start counting from. Because if I came over here and left it out in the center, then what I'll end up is I end up with minor divisions on that side and minor divisions on that side, and it becomes very difficult, right? You understand?
You count a full cycle.
So that's what we do. We count a full cycle, and it don't make any difference where you do it. So I could have had this sheet down. If you have the center line, you'll notice it comes up to be exactly the same. If I come now, I'm not in the center, but now it still comes up to be 1, 2, 3, 4, 5, 6.24. It comes up to be exactly the same. Y'all see that? So all you got to do to measure a cycle, it's the what? It's the same point on one alternation to the start point on the other. And that's the way you measure the time. Of course, we got this, we're keeping on this stuff. By the way, this is a computer. But the problem is, it's a digital scope, and so it's got a microprocessor in it, so it'll do a lot of the math for you. But these guys right here, this is like $450. You could get the same thing in an analog scope that uses a CRT for half the price. So that means you're going to run into a bunch of analog scopes out there. The problem is that they don't do any math for you. So they don't calculate the time for you. I mean, they don't calculate the frequency for you. This guy here does. So if you look at if y'all can read this, it says it's 69.6 per 60 hertz. So if we do the math, we should come up to pretty close to 60 hertz. So what would this come up to give me right here? It should come up to give you pretty close to 15.7 milliseconds. Yeah. And then if we take the reciprocal of that, so frequency is equal to reciprocal time, so frequency will be equal to I planned that.
You can't take it.
I was shooting for that. So frequency is equal to 1 over time. I wish I had a video of that. I'd have put that in place. So, so it comes up to be pretty close to 60 hertz, right? And I just pulled out my resistor. So this scope will measure peak to peak for you. It'll measure RMS. It'll measure all this stuff up. But you don't need to get used to that because and what's the peak to peak voltage? 12.6. Peak to peak voltage. What do we calculate right here? 17.8. So what we do on our scope to measure peak to peak is we adjust it till we get the bottom one on a flat line. So notice here I have minor divisions on top and I have minor divisions on bottom. So what I'm gonna do is I'm gonna take the position and move it. So here I'm doing the vertical position for channel 1, and I'm gonna move it till I get it on the line. I'm gonna count 1, 2, 3, 4, 5, 6. Wow, it's almost perfect. It looks like it's really close to 7. 7 divisions. I have it on 5 votes per division. So we should measure twice this, right? Well, that's P, my scope is measuring P.
What we at?
We're just trying to see,
Okay, so we on the board.
all we're trying to do is just figure out how.
Okay, so I thought we were still on the actual, lab.
No, we're actually measuring this. I'm just trying to show you how to use the scope. So BP would be equal, what does the formula say? It will be equal to BP times what? Times 2. So I'm gonna take this right here, 17.8, multiply it times 2. And what does that come up with? Yeah, and we're measuring 35. Well, either one of them's accurate. What the scope is actually showing you what's there, right? Understand? Okay, guys, what comes next? So we measured across the load. Oh, I'm sorry, we're drawing. So let me put it back in the center.
Are we doing what filter, the passer?
No, we're doing 32-1, the plots. What you got, your waveform is on your it's only got down, so you have to split that up. I'm right. You understand what I'm saying? Yes or no?
Yeah, man.
Well, no, you're just not going to. So we have 1, 2, 3, 4 divisions. We have 2 divisions. So you're going to take this, put it in 2 divisions. Or you're going to think that you're going to just like it right or not. Thanks like it. Let's see if we can get one more though. No, this is the best we can do. Yeah. Well, no, that's RMS. We're actually drawing the peak-to-peak value. The peak-to-peak value is actually almost 35 volts, right?
I thought,
An oscilloscope measures peak-to-peak. Period. Oscilloscope measures peak-to-peak. Our math is based on peak. So what we're doing is we're looking at what the oscilloscope is showing, right? So this is peak. My oscilloscope measures what? Peak to peak. So what we did is to go from peak to peak to peak. Peak to peak. We say it's just peak times what? Times 2. And I don't know why I did that. So what would that be equal to? What we come up with? 35 what? This is the peak to peak. This is the peak. So when I look at this and I'm measuring this, I'm going to, and how do we measure it? I'm gonna put this on a horizontal line, right? You understand? I'm gonna count in fives. Can everybody count fives? 5, 10, 15, 20, 25, 30, about 35 bucks. It's a little less. So that would be peak to peak with our scope is showing us, right? That makes sense now, Bernard? And then when I draw it, then the drawing is going to look something like this, right? So this is what we're seeing, right? Everybody understand that? Okay. And then we're going to take the same drawing. I'm going to look over to the pro and we're going to draw channel 2 relative to channel 1.
Let me ask you this, on this one, what we did peak to peak, why didn't we do the halfway instead of the full way on that drawing?
Because it's peak, it's the voltage, it's the actual voltage across the secondary.
Okay. I guess I should have read that.
So what's coming out of the transformer? Is it AC or is it DC? Is it pulsating DC or is it AC? Coming out of the transformer. It's AC. So that's what we're doing here. This is the voltage we're getting out of our secondary. Now what we're going to see when we hook over to our DC output, this is going to be stripped off, right? You understand? Yes or no? Okay, let me throw the DC up there. And it said, nope. I don't know. I think it's next. No, I don't know if we got to. Do we have a pencil sharpener? Can y'all see the two different colors?
Yeah. Channel 1 is the full way. Channel 2 is the halfway.
It's a lot prettier. No, it's moving around. So what you're going to do in the second drawing, you're going to do away with this, right? And draw one. So the first one on the left is the secondary. The second one is what? What's the drawing on the right supposed to be? Across the load. So the voltage across the load is the blue. So here's 0 volts. So this is never going down, right? So what I'm going to do is put this down here out of the way. Except it's still going to trigger. Yeah. So this should be your drawing on the what? On the one on the right, right? So this is what's giving us 5 volts right here, 5.13 volts right here. Alright, so what did we do? We stripped off the watt alternation. Got rid of the negative one, right? This is DC. This is AC. We call this pulsating DC because why? Because it's pulsing, right? So this is what you're going to draw on the watt via the load, right? That makes sense? Everybody okay?
Mm-hmm. Yep.
Y'all guys take a 10-minute break while I reset my computer so I can start using my pen.